So last Friday, I spent some time going over AP exam details. I didn't go through the entire handout here, but if you guys can spend some time reading through, I think these are just kind of tips and advice that I've kind of gathered over the years that I felt were beneficial and helpful for those, those of us who are preparing and getting ready for the AP exam. Just some just things to keep in mind. I went through the majority of it on the first page, but if you guys can spend time going over this, and also the next page, there's some duplicates here. But I think what I try to do is I try to highlight some common phrases that show up on FRQs and just what they mean and what they're asking for you to find. So maybe I'll reference some of these over the course of the week, but encourage you to read through this, and then back page as well. Just highlighting the distinction between all the different theorems in a short 1 or 2 sentences. Okay, some of the common phrases that indicate that you're working on a related rates problem potentially. Okay. Right, so I think it'll be good for you guys to spend some time going over it. But today, this week, I want to focus on FRQs. I think it's nice that even though students are in and out, it's nice that we have this AP exam being the second week. We still have one more week to kind of do some final preparations, and I figured that the most beneficial is just to go through as much of the FRQs as we can within the past 5 years. So we'll be looking at 2021 to 2016 FRQs. 2020 was kind of a strange year. It wasn't a full AP exam, so our AP exam was going to be more modeled after these other ones that we've had during most of the years. So every FRQ, there's 6 problems. I think each class, I'm going to try to go through maybe 3 of the more challenging ones, and then have the other 3 for you to do for homework. I am going to have help sessions every day this week, 3:30 to 4:30, and I figure that I can use each hour every day to finish off the rest of the FRQs that I didn't get to do in class. So I'll send you guys a remind Teams link this afternoon if you want to join, or if you can come into class. You can also come into class to join, or if it doesn't fit your schedule, I'll record it. You can always watch it as you're working through your homework if you like. So every day I'll be checking your FRQs, but there will be no late penalty. Okay, so I understand, with everyone's schedule, you may not be able to get to the FRQs in time. So there's no late penalty. However, I do find that if you can, if not possible, try to do all the FRQs on time, so that I think it's going to be the most beneficial to you if you're able to see all these FRQs before next Monday. Right? If you do it after next Monday, you kind of lose a little bit of the the helpfulness that we can gain from these FRQs. Okay. And then I will print out these 2012 and 2014 multiple choice tests, whole exams that College Board released. So I'll print those out hopefully by Thursday. I can print those out and have for you guys to practice. The key is on the website. You guys can work at your own pace, but I also want to be available as a last minute thing if you want to have any questions for me. So I will have a Teams help session Saturday and Sunday night. I'll record those as well, so you can always watch a different time where you can join in and watch you work through problems, or if you have any miscellaneous questions, I can answer those as well. Okay. Any questions about this week leading up to our AP exam Monday? Okay, so we're going to work through 2021 FRQs today. We'll at least try to get through 1 and 2, and maybe a little bit of 3. I will give you a little bit of heads up though. 2021, this FRQ is significantly more challenging than the other FRQs. So I don't want you to feel like, to be discouraged with how difficult this is. I think they did do a little bit of a different curve for this exam just because it was that much more challenging than the other AP exams. So, yeah, just I don't want you to think that, if everyone does poorly on the FRQ on these AP exams, then everyone's going to not earn a 4 or 5. But everything is scaled accordingly, depending on how everyone else does. So just to let you know that just be prepared that you're going to see these FRQs being a lot more challenging than the previous ones. But I think it's still beneficial that we go through each of these, even if it does feel a little bit different than other years. Okay, so number 1, the density of a bacteria population in a circular petri dish at a distance r centimeters from the center of the dish is given by an increasing differentiable function. So that's helpful. It's a smooth curve. The graph is always rising. F of r is measured in milligrams per square centimeters. Value of F of r for selected values of r are given in the table. Okay. So part A, use the data to estimate f prime of 2.25. So we have F of r. We're asking for f prime. We don't have a derivative for f. Well, we don't have a function to find the derivative, but we know that this is slope related, right? We can estimate the slope at 2.25. So we'll find the closest order pairs and we just find the slope that way. So f prime of 2.25. Change in f of r over change in r. Okay, we've seen this enough to be familiar with it. And numbers 1 and 2 are calculator active. Okay, calculator active for numbers 1 and 2. Okay, 4 divided by 5.5 is 8. Our units of measure, F of r is milligrams per centimeter squared, but it's per centimeter. You can also write it this. You can write it this way, or you can write it as milligrams per centimeter cubed. But basically, we're taking the units of the numerator and dividing it by the units of the denominator. We also need to be able to, using correct units, right, which we have, interpret the meaning of your answer. So we can say that the density, okay, the density is increasing, right? It's the rate of change of this units here. Okay, so we really want to be able to use these kinds of words to kind of specify what's increasing, what's decreasing. I think that's preferable to saying something involving acceleration. I know that that's naturally, we think of acceleration as the easiest way of connecting the second derivative, but in this case, acceleration is not going to make sense. And also, I would try to stay away from saying rate of a rate, right? I know I mentioned that before. I want you guys to understand that it is a rate of a rate, but they think they want to be more specific than just saying that. Okay, so we can say density. Here, I'll put this here. Make it easier to write down a little faster. Okay, density of the bacteria population is increasing by 8 milligrams per centimeter square per centimeter, or you can write it as 8 milligrams per centimeter cubed when r equals 2.25 centimeters, right? So we say density of a bacteria population, that's the milligrams per centimeter squared, is increasing. So we are representing the rate of a rate. So we're also writing it in a way that will earn us points. Okay, part B. Part B says the total mass in milligrams of bacteria in the petri dish is given by an integral expression, 2 pi integral r of f of r. Approximate the value using right Riemann sum. So this looks a little bit strange because I think this feels more familiar, right? If we see something like integral from 0 to 4 of f of r dr, this we can do because we will just say, okay, width times height of our f of r function, right? Our height is going to be coming from our f of r function, and that's, that is familiar. But that's not quite what it's asking for. It's asking for integral of r f of r. So we haven't quite seen this before on any of the FRQs, but we basically have to create a third column that represents this r times f of r. I mean, we have the information, it's just that we've never been asked to build another column, another row of information. So r f of r just says, let's just multiply each of the corresponding columns, right? R times f of r for 1 is just 0 times 1, which is 0. 1 times 2 is 2. 2 times 6 is 12. 10 times 2.5 is 25. And then 72 is the result of 4 times 18. The width, we're still going to do the same thing, right? We're still going to do subtracting each of the sub-interval x values for independent variables. So 1 minus 0 is 1. 2 minus 1 is 1. 2.5 minus 2 is 0.5. And then 4 minus 2.5 is 1.5. So Riemann sum, we know we're just going to have to find our width and height accordingly. So our width is going to come from these numbers here. And our height is going to come from this bottom row that we created. And so for these rectangles, we'll do width times height. We want right Riemann sum. So every rectangle, we're going to choose the y value on the right endpoint. So first rectangle is 1 times 2. Second rectangle, 1 times 12. Third rectangle, 0.5 times 25. And the fourth rectangle, 1.5 times 72. Okay, so as we do that, we're also going to be involving pi as well. So, but we'll leave that at the end. It's just the coefficient out in front, but really we're doing everything. Our work is mainly with this width times height, our right Riemann sum, right? Width times height, width times height. And once you find that approximation, we can multiply that by 2 pi. Okay, any questions so far? You can either leave your answer in terms of pi, or you can multiply that 2 pi through and get a decimal. If they don't specify, then you have the option. The reason why our units is in terms of milligrams is because if you look at each of these subsequent units that we have, radius is centimeters, f of r is milligrams per centimeter squared, and dr is radius, that's also centimeters. So you have centimeters times centimeters divided by centimeters squared. That's going to wipe all the centimeters out. You're only left with milligrams. So that's why our units of measure in terms of milligrams. Part C is the approximation, an overestimate or an underestimate. So we have an increasing function and what, left or right Riemann sum? Right Riemann sum. So create an increasing function, and if you make every rectangle where the right endpoint is hitting the curve and creating rectangles out of that, all these rectangles are what? Above or below? Above. So this is an over approximation. I think I made a mistake on my key. So my key says under approximation. I'll make it. I'll make that adjustment. I'll make that correction. But it should be an over approximation. Okay, part D. The density of bacteria in the petri dish between 1 and 4 is modeled by the function g, defined by g of r. For what values of k between 1 and 4 is g of k equal to the average value of g of r? So that's the key word. That's where we're going to start. We first have to figure out what the average value of g of r is. So average value, we're thinking average value theorem. Right? I got to build that value first. Okay, let me remind us what that formula is. 1 over b minus a. Average value, think of it as the average height. If I were to look at my g of r function, if I were to add up all the heights that it represents, what is the average height? What's the average value? So we know that we're looking at our bounds between 1 and 4. Our function is g of r, so put everything in place here. Okay, practice entering into your calculator. There's not, remember that the only variable that your calculator is going to be able to handle is in terms of x. Okay. Okay, so I chose to enter it under y1, so I don't have to enter all this onto the same line here. So I did 2 minus 16, parentheses cosine 1.57 square root of x, parentheses cubed. And then I went in and I typed in function here. Oops, sorry. Yeah, I typed this in here, so math 9, integral from 1 to 4. Rather than typing it all in, I can just refer to that function, vars y vars function, dx. Okay, 9.876. Okay, there's my average value. But the problem says, when is g of r, or in this case, g of k, equal to the average value? So we basically want to figure out, when is my g function equal to 9.876? So one option is you can graph the g of k function and the 9.876 and see where they intersect. Right? Definitely do that. But then that means you have to kind of play around with the window, try to get the window to fit so that you can see everything. Another option to do this is, why don't we just set everything equal to 0, and that way you can just look for the x-intercept rather than having to go searching all over for the intersection. So we can, why don't we graph this instead? Graph the g of k minus 9.876, put this in the calculator, and see where that graph is headed to, and see where that x-intercept is, and look for it from that perspective. So what I did was I went to y equals again. And then rather than typing all that in, I mean, you can do that minus 9.876, but I just referenced it y1 minus 9.876. And also because I did that, I highlighted my second equal sign, but I unhighlight the first equal sign. That just means that I can reference it without seeing all these graphs. I can just focus on just the calculator showing me the graph that I want to see. Okay. Window, you can adjust your window from 1 to 4 because those are x values. So you're only looking for an x-intercept between 1 and 4. Hit graph. And then you can look for your x-intercept using your 0 feature. So if you do second trace, 0, option 2. Choose a value to the left of the x-intercept, hit enter. Scroll to a point on the other side of the x-intercept, hit enter. You get 2.497. Okay, let's look at number 2. Any questions so far? Okay, here's number 2. Let's read through this together. Again, number 2 is also calculator. Okay, a particle P is moving along the x-axis, so it's only moving left or right, or motionless. Okay, those are the only 3 things that can happen. The velocity is given by Vp of t. Don't worry about that lowercase p. It looks like it's more complicated than it actually is. It just means that it's the velocity function for particle p. Okay, so basically v of t is sine of t to the 1.5. At time t equals 0, particle is at position x equals 5, so gives us a starting point there. Now there's a second particle that has its own velocity function given by v of t. So this lowercase q is just to reference that we have 2 velocity functions, one for particle p and one for particle q. Okay, at t equals 0, particle q is starting at a different position, starting at location 10 or x-intercept of 10. Part A, find the position of particles p and q at time t equals 1. So here, this is a particle motion problem where we have velocity, we have a starting point, and we're trying to find an ending point. So this formula that we reference a lot, that we use a lot here, this final position is equal to initial plus displacement. Shows up quite a bit, as we've seen in our past few weeks. Okay. So the formula is x of b equals x of a plus the integral from a to b of v of t, so displacement. So let's do this for particle p. The particle p, we were looking for position at 1. We're given position at 0, and then we want to figure out how much progress does this particle make between 0 and 1. So we can do the integral of velocity, which will give us displacement. And if we have displacement, we can use that progress to add on to the starting point, and that's going to tell us where the particle is going to end up. Okay. X of 0 we know is 5. The second portion can go into your calculator. Definitely practice using your calculator here. Integral from 0 to 1, make sure you're in radian mode. Always only use variable x. And we know that between 0 and 1 second, this particle is just going to move a third of a unit. So basically just 0.37, add that to 5. So he's starting at 5. Another second, he's only going to move 0.376. So he's going to end up x-intercept of 5.371. Okay, let's do the same thing for particle q. Particle q has a different velocity function, has a different starting point, but you can use the same formula here. Okay, so particle Q starts at 10. But when you enter this in the calculator, you're going to realize he's going to be moving backwards. He's going to end up at 8.564. 8.564. Part B says, are particles P and Q moving towards each other or away from each other? Okay, explain your reasoning. So what can we do to find the direction of motion of particle Q and particle Q, particle P and particle Q? What's available to us to figure out which direction this particle is moving? Okay, how can these velocity functions help us out with giving us that information? We could, but I think it's maybe a little bit easier here. We just want to know what's happening at 1, right? So what if we found the velocity at 1? How would that help us? So if velocity is positive, what does that mean? Okay, but for our problem though, what does a positive velocity mean? Moving to the right, yeah. And then if there's negative velocity, that means moving to the left. So if we know which direction these particles are moving, we can figure out whether they're moving towards each other or away from each other, right? So we'll use our calculator. Okay. Plug 1 into the velocity function for particle P. Sine of 1 to the 1.5, that's a positive number, so it's moving to the right. Particle Q, enter 1 in for T, we get 1 minus 1.8, that's a negative number, times 1.125, that's a positive number. So negative times positive is negative. So particle Q is moving left. Okay, so particle P starts at 5.371, is moving right. Particle Q it's at 8.564, moving left. So are these particles moving towards or away? Okay, so I think sign line not in the sense of we're testing intervals, but sign line in terms of visually seeing where these particles are headed, right? We know that particle P is 5.371, moving to the right. Particle Q is at 8.564, moving left. So we can conclude these particles are moving towards each other, right? Towards each other. Okay, so here's the justification that I wrote down. At t equals 1, particle P is at position 5.3, moving right. Particle Q is at position 8.5, moving left. Therefore, the two particles are moving towards each other at t equals 1. Okay, part C. Find the acceleration of particle Q at time t equals 1. So acceleration, what can we do to get to acceleration? Yeah, derivative of velocity, right? So now we're just looking at particle Q. We're not looking at particle P anymore. It's just particle Q. So if we know the acceleration of particle Q, we can figure out the speed, whether speed is increasing or decreasing, right? We can compare the signs of velocity and acceleration. So we'll go to particle Q and find the derivative of particle Q, make the calculator do that work for us. So there's that feature of Math 8, that n-deriv feature that allows us to evaluate the derivative at a point. So I can do x minus 1.8, type in the velocity function, give it the t value, and then make the calculator find the derivative, the acceleration at that point for for us. So our acceleration is 1.026, but our velocity is negative. So what does that tell us? Speed is decreasing, yeah. Yeah, we have this information from the previous part. Acceleration we just found, positive. So negative velocity, positive acceleration. The signs are different, so speed is decreasing. Okay, part D. Part D says, find the total distance traveled by particle P over the time interval from 0 to pi. So what formula do we have for total distance? It's similar to displacement, but we have to involve what? This is where our calculator can really help us out. Integral of the absolute value, yeah, total distance. So it's actually part D is actually the easiest part of this problem. We just set it up and put it into our calculator. Now, even though this is relatively easy, anybody know what is a common mistake that I see happen a lot when students are asked to do total distance? Has to do with this formula here. Final position equals initial plus displacement. I think what students do is they see we use this formula so much that we think that total distance would just be the absolute value plus the initial, right? But if we're asking total distance, we don't care about where you're starting from. We just want to know how much progress you made in that time interval. So total distance, we don't add the initial. We just do the absolute value around the displacement, and that's it. So I see a lot of students do this. They want to do initial plus this, and that's not total distance. Okay. Okay, number 3. Okay, number 3, a company designs spinning toys using a family of functions where C is a positive constant. The figure shows the region in the first quadrant bounded by the x-axis in the graph of y equals cx, root 4 minus x squared. That's this curve here. Each spinning toy is in the shape of a solid generated when such a region is revolved about the x-axis. So if you can imagine this rotating about this x-axis, it kind of creates that kind of spinning top shape that is lying on its side. All right, part A, find the area of the region in the first quadrant bounded by the x-axis and the graph for c equals 6. So we have our c value, which is 6. We can go ahead and update our equation here. So we'll let our function okay, we have our c value updated, so we know that's the function. It says ask find the area. So the area, just think of it in terms of top minus bottom, that's the most straightforward one. So top minus bottom. We know the top is the curve. We know the bottom is the x-axis. Here's our formula, top minus bottom. Right, so top is the curve, bottom is the x-axis. What are the bounds going to be from 0 to this point, right? So how can I find this bound that I need? No, this is number 3 now. This is non-calculator, so we can't just plug in the calculator and find that x-intercept. We can just do what? Set equal to 0, right? Set equal to 0. We don't want to plug 0 in here. We want to set, well, the y equal to 0, right? Okay. It's already in factored form. If I set 6x equal to 0, I get 0. But if I set that 4 minus x squared to the 1/2 equal to 0, I can solve for x. Take the square of both sides. Solve for x. I get plus or minus 2, but only 2 makes sense because negative 2 is all the way over here. Right? So we know we're going to go from 0 to 2. Top minus bottom. Top is the 6x root 4 minus x squared. The bottom is 0, so minus 0. But I'm going to leave that minus 0 out. I'm just going to close it with the x. Okay, we want to find the area here. This is non-calculator. Look at how this is set up. What's involved here if I want to take the antiderivative? What does that look like to you? Yeah. So typically we want to try to expand and use power rule, right? But we can't expand this through the radical. So, but our first option is always power rule, right? Expand everything out and do power rule. But this is too complicated for us to do power rule. So our second option for antiderivatives is always going to be use substitution. So we'll explore use substitution here. Let me rewrite this using parentheses to help us spot the u value a little better. Okay, what could be our u value? Yeah. And that power is favorable, right? That x squared is favorable. We know that the x squared is going to take care of this x. It should work out nicely. We'll go through our process. Make our substitutions here. X's cancel out. Push the coefficients out in front. And we should be staring at a much easier problem. Okay, so now that we've taken care of all the mess in terms of u, we can now rely on what rule? Power rule now, right? Add 1 to the exponent divided by that exponent. Do some cleanup. We'll flip that fraction, bring the original variable back, and then we can work the bounds in. Threes cancel out. The negative 2 is going to stay. Bring the original variable back. And now half bracket to now work in the bounds. Upper bound first. Minus the lower bound. Sorry, 4 minus 0 squared. Four to the 3/2, that's same thing as square root of 4, which is 2. 2 cubed is 8. 2 times 8 is 16. Okay, I will go through parts B and C in the help session today. Your homework is the rest of the FRQ problems for 2021. So 4, 5, and 6. I'll send out a reminder this afternoon. But again, if you are not able to finish, I'm still checking homework tomorrow. But if you don't finish, you can just show it to me later. I won't give. There's no late penalty. But the hope is that we can try to do 6 FRQs a day between classwork and homework, so we can see all of these FRQs before next Monday. Okay. Help session this afternoon, and the key is on the website, and I'll also upload these videos on the website as well.